sight becomes story.
See better, shoot better, create better.
You got the camera! Now get the vision.
The visible light spectrum and color wavelengths. In this episode, we'll decode color at the physics level and then explore how light becomes color. We'll map wavelength to hue and explain why daylight and tungsten feel differently, and show how sensors translate spectrum into colors that we grade later. Now, color isn't an extra property that is added to light. No. It is baked into the wavelength of light itself. Now, color is what? Simply light at different wavelengths. Color is simply light at different wavelengths. You get? Now, let's break down how those wavelengths translate into colors that we see and that we capture. Let's look at part 1, the visible spectrum. The visible spectrum is a narrow band of electromagnetic spectrum, as we have discussed earlier, that our eyes can detect. It spans from wavelength of roughly 400 nanometers at the violet end to 700 nanometers at the what? The red end. These are their wavelengths. Now, at the short end, around 400 nanometers, we see what? Violet and blue. These are higher energy wavelengths. At the long end, around 700 nanometers, we see red, which carries less energy. Outside this window, we get infrared and ultraviolet. But our eyes and cameras filter and block them to keep our colors predictable, because we don't need them in our photography. We don't see them. So white light is simply a mix of all these wavelengths together. So when you see white light or hear white light, it's a mixture of all these different wavelengths of light or all these colors of light. You get? Now, when white light passes through a prism, I've showed you a prism before, or through raindrops in the atmosphere, it separates into the familiar rainbow. That is a proof that color is already in light, white light. You get? Human vision and cameras. Now, the human eye has 3 types of cones, sensitive to red, green, and blue light. Our eyes detect the light spectrum. These 3 types of cone, red, green, and blue, with those receptacles, or what we call receptors or cones. That's what our eye uses to detect them. So our eyes has what? 3. That is what is used to detect light, all the colors we see. Cameras mimic this same system of RGB. RGB simply is red, green, and blue. So there are filters that are placed over sensor pixel. Remember, we have sensor pixels, then we have the filter, the RGB filter on top of it. That array is what we call a Bayer filter array. You get? Now, where each pixel only records one color of light. Together, the camera then reconstructs the full color image. How? By combining those three signals. But camera doesn't always interpret wavelengths the same way that we humans do. That's where white balance comes in. As photographers and cinematographers, I always talk about white balance, white balance. But do we ask ourselves, how does our eye do white balance? You get? So that's the limitation of technology. So it means something has to be put in place to actualize white balance. Now, what does it do? White balance, what we are trying to say is that it adjusts how the camera defines neutral, shifting the image either warmer or cooler. This is a powerful way also to control mood. Now, filters, gels, and post-production grading all work by what? Changing the balance of wavelengths, that is color, captured and displayed. Part 2, spectral power distribution. Now, spectral power distribution is in short form called SPD. SPD, spectral power distribution. What is it? A light source isn't just warm or cool. It has an SPD, how much energy it emits at each wavelength. So there's an energy for each wavelength. You get it? Now, daylight has a fairly continuous SPD. Tungsten leans heavily toward longer wavelengths, so of course it's going to be warmer. Cheap LEDs can have spiky and uneven SPDs that cause odd skin tones when you are under them. So we should be careful how we use cheap LEDs, cheap ones. High quality LEDs boost high CRI and TLCI. I put these definitions on the screen for you to see, because they better cover the visible band. Let's look at sensors and color filters. Now, digital sensors are mostly monochrome. Yes, they count photons. That's all they count. Color comes from micro lenses and color filters, like we talked about the Bayer. We're going to look more into that. This sample light through what? The red, green, and blue filters. Now, your raw converter reconstructs the full color pixel via what we call the Demosaicing, which we're going to talk about very shortly. Now, if the SPD is uneven, one channel may be starved, producing color cast or, banding in what? In deep corrections. Now, what is the Bayer filter array? The Bayer filter array is a crucial component found in almost all modern digital cameras. Now, like the DSLR and video cameras. What is its purpose? It is to allow a single image sensor, which is inherently color blind. It doesn't know color. It's just grayscale. It can only measure the intensity of light. You get? Not color. So this allows it to capture a full color image. Now, I'll do a layman's explanation followed by an illustration. And you see this on your screen. Imagine your camera sensor as a massive grid of tiny solar panels called, pixels. When light hits the sensor, these pixels, record how bright light is, but they can't tell the difference between red, green, or blue light. They only see in shades of gray. To capture color, a special mosaic, like a mosaic called the Bayer filter array, is placed directly over that sensor. You get? Now, this array is a pattern of tiny colored filters: red, green, and blue. How it works: the Bayer pattern is a repeating 2 by 2 block of filters. So when we say 2 by 2, we are talking about something like this: 1, 2, 1, 2. So the Bayer pattern is a repeating 2 by 2 block of filters. It's structured as how? 50% green, because 2 of the 4 are covered with green filters. Now we have 25% red, because 1 pixel is covered with a red filter. Now the next one, 25% blue, because the other remaining pixel is covered with a blue filter. Now, when light hits the sensor, a pixel covered by a red filter only measures what? The amount of red light that is coming in. A pixel covered by a blue filter only measures what? The amount of blue light that is coming in. Now, a pixel covered by, those 2 pixels covered by the green filter only measures what? The amount of green light coming in. Therefore, after the light is recorded, every pixel only has 1 color value, either a red, green, or blue, and missing the other 2. Why more green? The pattern is called RGGB. The reason for having twice as many green filters as red or blue filters is to mimic the way the human eyes, our eyes, how it works. Our eyes are most sensitive to green light, if you don't know that. Now, and green light also provides the most information about brightness and detail. The extra green pixel help the final image appear sharper and more natural to us. Let's see an illustration of the Bayer filter array, the structure, and how it sits over the photo sensors. Now, let's look at an incomplete picture first. Now, the Bayer filter uses a repeating pattern of colored filters over the camera sensor, as I've discussed, which are mostly arranged in what? 2 by 2 block, which we've called the RGGB. The red, green, blue. Red, green, blue. Now, if you look at the entire array, the RGGB block, there are a total of how many? 12 color values you need. Now, if we have 4 pixels, that just like I've showed, and 3 colors each, what happens? You have 12. 4 times 3 is 12. You only capture the 4 values that are shown. Now, this is why a lot of people often say 2/3 or about 67% of the color data is what is missing. Now, the figure of 75% is just an approximation that people use. Why not capture all the 3 colors. Cameras or camera makers choose this. It's a compromise for two main reasons, two major reasons. That's why they use this simplified approach. Why? Cost. Of course, cost is a factor in many things we do. And what? Simplicity. So what you have, you just need only one sensor and the Bayer filter on top of it. So that's very simple. Now, the main goal is to use a single, simple, and inexpensive CMOS or CCD sensor. Those are types of camera sensors. Now, the only way to capture all the 3 colors at every single pixel is to use a much more complex and expensive design if you want to go that route. Now, we have the 3 cheap cameras. They use a prism to split light into red, green, and blue beams, and sending each beam to its own separate sensor. We also have another method called the stacked sensor, or some people call it the foveon. Now, it's layering sensors on top of the other, which is physically difficult, to manufacture. The Bayer array, as we can see, is the simplest and the cheapest way to get color from a single sensor. Now, matching the human eye, which has more green. The array contains twice as many green filters as red and blue. Like we saw, we have only just one red, one blue, but we have 2 green. This is deliberate because the human eyes, like I said, is most sensitive to green light, and it uses the majority of details and brightness. That is what it uses for details, for brightness, for luminosity. So by dedicating half the sensor to green, the camera ensures it captures the highest possible detail and brightness information, which is critical for a sharp and realistic image. Now, the missing arrow and big color detail is then estimated. That is a process we call Demosaicing from the surrounding pixel. Now, I'll show you an example of that. Now, the missing color data is not a sign of poor quality, but a clever engineering trade-off to get high resolution, full color image from a simple and affordable sensor. To see the technical details of the Bayer pattern, watch this clip capturing digital images.
Digital images may look simple on our screens, but inside the camera, something very interesting is happening. Before the camera can store an RGB image, it must first capture light from the real world. In modern cameras, this is done using a CMOS or CCD sensor. This sensor is a photosensitive surface arranged in a grid. Each tiny point on that grid records how much light hits that position. But here is the problem. By itself, the sensor only knows brightness. It can tell how much light arrived, but it does not naturally know whether that light was red, green, or blue. So without a color system, the camera would only create a black and white image. To solve this, cameras place a tiny color filter over the sensor. This filter allows each pixel to receive only one color of light, red, green, or blue. The most common arrangement is called the Bayer filter array. In this pattern, the pixels are arranged in repeating blocks of 4, red, green, green, and blue. This is often called the RGGB pattern. Notice that there are 2 green pixels, 1 red pixel, and 1 blue pixel. Why more green? Because human eyes are more sensitive to green light. We also detect brightness and detail more strongly through the green channel. So, By capturing more green information, the camera can produce an image that appears sharper and more natural to our eyes. But there is another challenge. Each sensor pixel only captures one color. A red pixel captures red only. A green pixel captures green only. A blue pixel captures blue only. However, a normal image pixel needs all three values: red, green, and blue. So the camera must estimate the missing colors. This process is called demosaicing. Demosaicing is the process of taking the Bayer pattern and converting it into a full RGB image, where every pixel has red, green, and blue information. The camera looks at nearby pixels and makes intelligent guesses. For example, if one pixel captured red but is missing green and blue, the camera checks surrounding green and blue pixels and estimates what those missing values should be. Basic demosaicing simply averages nearby values, but modern cameras use more advanced methods. They try to preserve edges, reduce color errors, and keep fine details sharp. This is why RAW files are so powerful. When you shoot RAW, you are saving much more of the original sensor information. Then software like DaVinci Resolve, Lightroom, or Camera Raw can apply different demosaicing and color processing methods. But the Bayer filter also has limitations. Because every pixel does not capture full color directly, fine, repeating patterns can sometimes create strange color artifacts, false color, or moire. This is one reason why some fabrics, screens, lines, or striped textures can look strange on camera. So the Bayer filter is a beautiful compromise. It allows modern cameras to capture color efficiently using only one photosensitive sensor, while relying on smart processing to rebuild a full-color RGB image. In simple terms, the sensor captures brightness. The Bayer filter separates color. Demosaicing rebuilds the full RGB image, and the final result is the photograph or video you see on your screen. This is creative vision, helping you see better, shoot better, and create better stories.
Now, creating the final image. Since the raw data from the sensor is incomplete, i.e., the red pixel is missing its green and blue values. You understand? The green is missing the other one, this one is missing the other one. The camera's internal computer has to fill in the blank spaces. This process is called demosaicing or debaying. Now, the camera processor uses a complex algorithm to look at a single color value of a pixel and compare it with the color values of its immediate neighbors. So it looks at this one, it compares it. This one, why is it only green? Why is it only blue? It must contain the other one. So it looks at its neighbors and does a calculation to get the blue. If it is red, to get the blue and the green. You understand? Now, it intelligently interpolates the missing green, the missing red, and blue values for every single pixel to create the final full color photograph that we all see. Now, demosaicing is the essential step where our camera's processor take the incomplete raw color data by the Bayer filter array and figures out the full color of every pixel, turning a mosaic of single colors into a complete image. That's what I've just been saying. Now, let's look at demosaicing again. Let's think of the data coming off the sensor as a giant jigsaw puzzle where 75% of the pieces are missing their color information. So just to explain why I say one color is missing, the other color is missing, I'll use this table. Now, let's say we have the pixel, we have the raw data, and then we have the missing colors. What is a pixel? We take, for example, the red. Just like you can see on this, we take the red, Now, what is red missing? Red is, it has, what does it have? It has the red value, of course. The red filter will collect red values or red color. Now, what will it be missing? It will be missing the green and the blue. What about the pixel green? So pixel green will have only green values. What will it be missing? It will be missing red and blue. Now, what about the blue pixel? It will only be collecting blue values. What will it be missing? It will be missing red and green. You get it? Now, the Bayer pattern shows the raw data where each pixel has only one color. That's what it shows. Demosaicing image shows the final result after the processor has estimated and filled in the missing color components for each of those pixels, just like I described, which result in a continuous full color image. Let's look at color in cinematography. Not too much of science, not too much of technical things. Now, color temperature affects our mood. Warmer tones like red and oranges, they create what? Intimacy and comfort. While cooler tones suggest isolation and tension. White balance lets us what? Control how your camera interprets the color, either to reproduce exactly what it is, the reality, or to create a mood. That's what people do in cinema. When they say this is cinematic, they try to create a mood. But that is not the real thing that was there. You get? So when you talk about color grading, you're almost talking about white balancing. Now, it gives you practical control. So white balance moves the neutral point. So white can look like white, if that is what you want. Now, a 5600 Kelvin preset suits daylight, because that is the Kelvin value for daylight, while a 3200 Kelvin suits tungsten. So when you tune your light value to that, you get that warm feel, that tungsten feel. Now, when sources mix, decide which one to honor. You have two different types of light. And then gel. Which one do you gel? To control it to match the other one. Or which one should you turn off? You understand? Now, for the best skin, choose lights with a smooth SPD. And set a custom white balance with a gray card. Now, what is a gray card? A gray card, you can buy it. It's something like this. I have some. This is a gray card. You can use it and set your white balance. You snap it. That's a function in your camera. When you snap it, you tell it that you should use it to balance the color, because this is what actually used for color balancing. The camera thinks that this is pure white, but this is a gray card. Now, Sony cameras, if you see their covers, they make it gray. So you discover that you can actually use the Sony camera lens covers to do your color balancing. Now, finally, we have seen that as photographers or film makers, that we are not just capturing colors. We are shaping feelings. A prism can split white light into all its component wavelengths, as I've always showed. I've talked about the prism that gives us what we call diffraction grating to display a mini spectrum. Now, compare a face under daylight LED. You can try this. A face under daylight LED versus a cheap LED versus tungsten. Show white balance and a gray card fix. So what I'm trying to say is that put your face or a face under these different types of light and try to balance, get the same face in your picture by doing what? Using that your gray card to get the white balance out of each of those colors, so that the final image you get when you you have those colors on the faces, is still the same. You understand? Now, show a color checker chart to demonstrate accurate profiling. See how the same scene can feel warm. Try to do this, and cozy or cold and clinical, simply by what? Reinterpreting wavelengths. So these are some key takeaways you can try out. Now, in summary, we have seen that color is nothing but wavelength. The visible spectrum spans 400 to 700 nanometers. It maps directly to our perceived hues. Real-world light sources, we have seen, they differ by what we call the SPD. Continuous spectra yield more natural color. So any light that has a continuous spectra is better. Sensors, they need color filters. That's one of the things you have seen. And Demosaicing, because of the shortages or the limitation of the technology, because of consideration of cost, and all of that. Now, uneven spectra stress one channel and complicate grading. We see that we use good quality lights and proper white balance for consistent and flattering color. We have seen blue and violet light that they are shorter and they have more energy. Red light has a longer wave and therefore it has low energy. Now, cameras, we have seen, what do? They mimic the human eyes, the human vision with RGB filters. But white balance defines the mood. Finally, we've seen that by controlling wavelengths, we control color, atmosphere, and emotion.
Creative Vision. Podcasts, tutorials, and lectures.
Where photography and drones meet cinematic magic. Surveying, mapping, inspections. See the future.
From sight to story.
Sight to story. See the future.
From a simple thought to a tangible reality. Witness the transformation.
See better, shoot better, create better stories.